So now, after completing the central processing unit, we move to the memory section. Okay. So we are going
Yes.
to cover this. We are going to cover the register, that is the top level of the memory, then the cache memory, then the main memory, your RAM, and then hard disk. This is the one thing. So we are going in deep what these things are. Another thing is this: the size of the memory, bits and bytes. So it goes like this. First is the bit, then after bit there is the byte, after byte there is kilobyte, then megabyte, then gigabyte, then terabyte, then petabyte. So in the class I already told you that bit means a switch that can store 0 or 1 bit. This is known as a 1 bit, either 0 or 1. That is 1 bit. Okay, and eight such bits make 1 byte. So if you have, like, you have 1, 2, 3, 4, 5, 6, 7, 8. So to store this number, you need, what is the size of this? 1 byte. Okay.
1 byte.
Okay. Because each the 0 or 1 takes 1 bit. Okay. Get the point?
Yeah. So 8 bits is a byte.
Yes, 8 bit is a byte. So 8 bit means a byte, 1 byte. Okay. So generally in the notation, if I say small b, that's mean bit. Okay. And if I put the capital B, it means byte. Okay.
Byte.
Yes.
Yeah.
If we use the uppercase B, it means byte. So this is the one thing. Now, this is the only difference here. From bit to the byte, you require 8 bits. So 8 bit makes a byte. But when you move from the byte to the kilobyte, it's 1000. Okay. So 1000 byte means 1 kilobyte. But it's not technically correct. Technically this number is not 1000. It's the wrong number. Correct number is 1024. Okay.
Oh.
But because 1000 and 1024, they are just similar, only 24 higher. So we generally say this 1 kilobyte is 1000 bytes, especially in the networking terms. When we are talking about the internet speed or something like that, we are not going to care of is it 24 bits. For 1 kilobyte, we say 1000 bytes, but actually it's a 1024 bytes. Okay.
Yes, sir.
So in 1 kilobyte, you have 1024 byte. So if you have 1024 byte, it means you can write it like 1 kilobyte. Getting the point?
Oh, yes.
And then from kilobyte to megabyte, again it's 1024. So 1024 kilobyte is equals to 1 megabyte. Okay. And then 1024 megabyte means 1 gigabyte. And 1024
1 gigabyte
means 1 terabyte. So it's just at this
1
place,
terabyte.
this number is 8. Otherwise, it's just a 1024. Okay. So if someone asks, how many kilobyte in a 1 megabyte? Answer is 1024. How many megabytes in a 1 gigabyte? Answer is 1024. How many gigabyte in a 1 terabyte? Answer is 1024. Okay. But how many bit in a 1 byte?
So the number The number is just 1024 going straight from kilobyte to
Yes,
megabyte to gigabyte to terabyte.
yes. But from bit to the byte, it's 8. Okay.
Yeah.
Yeah, that's it. So that's I cover here the size of the things. Okay.
All right, sir.
So there are a lot of sound. I think some TV is going on, or yeah. Okay. Now it's okay. Mark, are you
Yes,
hearing me?
sir.
Okay. So this memory is normally
Yeah, yeah, hearing you clear.
okay. So this memory is divided into the primary memory and the secondary memory. Okay.
Secondary memory.
And then primary memory is divided into the RAM and the ROM. And then again, this RAM is divided into the SRAM and DRAM. ROM is divided into the PROM and EPROM. We go in the deep in the next slide. So secondary memory is like your hard disk, your SSD, CD or DVD, or flash drive. Now you may ask the question, why we need so many types of the memory? Any idea? Because I am going
I'll
a lot of type of the memory. Why we need so many types of the memory?
Well, for one, the secondary memory is physical
Hmm,
memory used to store information permanently,
that's true. That's true.
and the primary memory, basically the RAM and the ROM, is the memory that helps the programs of the computer to function. I would assume.
Yes. So, let me open change from here. Let me move to here. Yeah, I know this thing. So, see, now when we defining the computer system, uh, okay. So, thing like this, you need three things: uh, a processor, CPU, okay, and
Mhm.
some input devices, some output devices, because input you provide, and this is the computer, your computer basically. It has a CPU and it generates some output, and in meantime it has some program also. So where we store the program, it may be program or it may be your data like your video files or Excel files or PowerPoint files, anything that is also a data. So you have two things here, a program and data. Okay, where you store these program and data?
Mhm.
In memory.
They stored on the secondary
Yes,
and the secondary
that's
memory.
true. You need some memory. Again, you already know. And CPU, when you provide some input or CPU, take instruction from this memory and data from this memory and execute it and then generate some output. Okay, like I say,
Mhm.
Mark, you just write, you just prepare a PowerPoint. How you do? You take a PowerPoint program and then you design something there. So when you instruct something to the computer, computer utilizes two things, the program and the data. Okay, it use its own program to
Mhm.
manipulate the data and your input and generate some output. But the problem lies here. What is the speed of your CPU? You already studied about this thing. Something like 2.0 billion instructions per second. Yes.
Yes.
And what is the speed
Mhm.
of your memory? It's a very less. Okay. So if
All right.
now the problem lies here, your CPU works at the speed of 2.0 billion per second, while your memory is a very slow. Okay. Like your hard
Yeah.
disk, your hard disk is very slow. It, you can just read thousands and thousands or 2,000 instructions in a 1 second. That's the your memory speed. and your computer, your CPU speed is 2.0 billion per second. So there is a huge gap between. Now, if you have, if you can afford a memory that is the speed of this CPU, that's the best thing. If you have some such type of the memory, but if you construct such type of the memory element, its cost is what? Huge. Okay,
Mhm.
you getting the point? So if you construct a memory that's,
Yes, sir.
you construct a memory that's speed matched with your processor's speed, that's the two good thing. But the cost of that memory is very high. It's very high. Okay, and
It'd
then
be expensive.
yeah, expensive, and nobody can afford this computing that type of computer system. So what's the solution arrive? Developed. Solution is developed like this. Okay, you have a CPU. I give you a small amount of fast memory. Okay,
Mhm.
the speed of this memory, fast
Yeah.
memory, match with your CPU speed, and then a larger memory but smaller speed. So this memory, this is the first level of memory, first level memory. This is the second level of the memory. So the speed of second level memory is less than first level memory, but the cost of second level memory is
Mhm.
less in comparison to the first level. So as go deeper and deeper, the size increases. It, I think it's coming in the next class slide. So as you go deeper in the memory hierarchy, the cost is decreasing, size is increasing, but the speed
But
is
the increases
speed is decreasing.
decrease.
Yes. So that's the concept. That's the reason why we need uh, this much. This is that's the reason why we yeah. Let me out from here. Okay. So that's the reason why we need these much type of the memory. Otherwise, if someday comes when you can construct a memory that matches the speed of the CPU and cost is also low, then you don't need these much of the memory. Okay.
All right.
So that's the thing. So primary memory is the faster one, secondary memory is the slower one. That's the one level. Okay. Let me move to the next slide.
Yes, sir.
So what is the, okay, so what is, okay, there is two things. When you say in your computer there is a RAM memory. Okay, so that is the special thing, RAM memory. And there is also a special type of memory that is known as RAM or random access memory. But the point is, your RAM means computer's memory is also a RAM, that is random access memory. Okay, it may be a little bit confusing. So your, this RAM here, whatever I write here, this RAM, okay, this is the type of a memory.
Yeah.
Okay, that is random access memory. But your computer also has a memory that's called RAM. Okay, and this memory is also a random access type of memory. Okay, it's clear or not? I think it's a little
Yes.
confusing. It's a little bit confusing, but random access memory is a type of memory where you okay, so suppose this is the memory. Okay, okay, let me move from here so that it's confusing. Okay, let me move here so that I'm going to make it clear. Okay, okay, suppose uh, this is the some rack where you have a book. Okay, these are the books. So this is your book number 1, this is your book number 2, this is your book number 3, this is your book number 4. Okay, okay, suppose you, I ask you, Mark,
Mm-hmm.
please bring the book number 1 for me. How you bring this book 1? You remove this book, so you remove this book 4, book 3, book 2, and then you take this book 1 and give to me. That's the point. Yes
Book
or no?
one. Yes, but I can't just remove book one and let the other books come down, or
No, you can't do like that because you don't know how many books are. I'm just taking the 4 examples. It may be 4,000 or 4 billion books.
oh,
Okay, so you just I'm just saying
Alright.
you are sequentially removing one by one by one, and once you reach to that particular book, you take
Uh-huh.
that book and bring to me. Okay, so when the CPU demands something, some data, suppose it demands for this B1. So to take this B1, you have to visit here. Okay, this is not B1, this is not B1, this is not B1. Okay, this is B1. So I will back it to the CPU.
Mm-hmm.
But to reach up to the CPU, you have to go through the B4, B3, B2, and then you arrive to the B1. Yes or no? Yes?
Yes.
Now, if I ask you to bring the book 4, then it's just easy. Take the first
Uh-huh.
book, and that is the book 4, and you bring it. So these all the locations does not have the equal amount. So if this has the smallest amount of time to access, and this has the, in this example, this is the largest time. It takes largest time here.
Yes.
Okay. So this is known as sequential access. Okay. This is known as a sequential access, where you go one by one. Or in other words, to access this element take different time, to access this element take different time, to access this element take different time. To accessing any element take a different amount of the time. That is the point where sequential access makes. Okay,
Oh, yes, sir.
am I clear?
Yes, sir. Yes, sir.
So that is the sequential access. Now, what is random access? What is random access? Suppose this book arranged like this. Here you put a
Oh,
book 1, then you put a book 2, then you put a book 3, you put a book 4. Now to access the book 4, you can directly take this book 4 without making any difference to book 1, book 2, book 3. Yes or no? It's not horizontally, but it's just a parallelly. You put at all the books. Now it's easy to bring any, if you want either book 1 or book 2 or book 3 or book 4, it takes
book
equal
2.
amount of time. Yes or
Yeah.
no?
Because it's random. Yes.
Yes, that is random access. You bring, you have to take a, means in random access, to take any data from any location, take the same amount of the time. That is random access. In sequential access, from to bring the data from the different location, take the different amount of the time. So which one is better, random access or sequential access?
Random access.
Random access is better, but again, this goodness has its own cost. So random access is costly in comparison to the sequential access, but it's fast. Okay, so the memory which support this random access is known as random access memory. Okay, any memory that support this random access is known as a random access memory. Okay,
Alright, sir.
and in your computer, there is a memory that is known as RAM. This RAM is a type of random access memory. It supports random access. Okay,
Mm-hmm.
good. Now I move to the slides again. So now I move to, so now it's clear, I think. Uh, RAM supports random access. Okay, because we already defined this random access concept. It access from any
Mm-hmm.
location in the same amount of the time. This RAM or random access memory is classified into two types, SRAM and DRAM. Okay, notice this definition. Read and write can be performed in any order and it takes the same amount of the time. Yes, that is the concept of randomness. You can access from any location or writing at any location. It takes the same amount of the time. Okay, and then again, RAM is a volatile memory, as the as the data lasts when the power is turned off. So it's a volatile means as the power turned off, the data is also turned off. Okay,
Gone.
data is gone. Yes. Okay. So what is SRAM? So just it consists of the 6 transistors. Okay, and I'm
Six
not going in detail.
transistors.
And this is not, I'm not asking to this question how many transistor requires, but in theory you remember this thing. SRAM is 6 transistor, and this DRAM is 1 transistor and 1 capacitor. Okay.
One capacitor.
uh,
Yes, sir.
SRAM is a more expensive, it is faster, it consumes less power, and this one is the important one. Hold contents as long as power is available.
This content
Okay.
wrong
Now
is
see,
available. Yeah.
see this DRAM concept requires recharge after every few milliseconds to maintain its data. Remember here this definition. See this definition. RAM is an volatile memory as the data lasts when the power
Memory.
is turned off. So either in SRAM or in the DRAM, as the power gone, data is lost. But in SRAM,
Gone.
in both SRAM or DRAM, data is gone in both. But even the power is on, okay, even the power is on, content is available, okay. But in SRAM, but in DRAM, even the power is on, you have to recharge the memory so that the data is available, otherwise data lost. Getting the point?
Yes, sir.
So this is coming from some electronics thing, because these capacitors requires charging after some millisecond or microseconds. Therefore, in DRAM you have to recharge after after a few milliseconds, so that your data is not lost. Otherwise, your data is gone. Okay, so that is the difference. And again,
Yes.
because you need recharge, this is the slow, and that's why it's a less expensive also. Okay. Good. So register is the fastest memory. There is no memory that is faster than the register. So it is the fastest memory. Okay. Again, it is a static random access memory, or it is SRAM type. Okay. Register is the top level fastest memory.
Yes.
Again, same thing. CPU always load data and instruction to the register before performing any operation. Means CPU directly operate on these registers. Okay. So before performing any operation, data first move to the register.
Yes, sir.
Then CPU performs the operations. Okay. CPU directly manipulates the content of the register memory. Means it's either reading or writing something. First it read or write into the registers, and then the data move from the register to the lower level of the memory. Okay. Size of the register is measured in the number of bits they can hold, and generally the size is 32-bit or 64-bit based on the registers. Okay.
64.
Yes, 32-bit register or 64-bit register. And then the processors often contain several kinds of the registers. Any question up to this point?
Register static. Register no, straightforward. I was really trying to remember.
Okay, good. Okay, good. Then the cache memory. Okay, so register is the static RAM. Register is the static RAM, and see, cache memory is also a static RAM. Okay, so your two fastest memory are of type static RAM. Okay, register is the fastest, and cache is the second fastest type of the memory. Good. Then remember this statement. It's okay. So cache is the static RAM. I'm going on this point later. All modern CPU have multiple levels of cache. This, remember this term, it's all. Currently, you find any CPU, it have a multi-level cache memory. Generally 3, L1, L2, or L3. If you remember when I show you the task
L3.
manager, you see these 3 levels, L1 cache,
And
L3 cache.
the
Yes.
L1 and the L2 and the L3.
Yes. So these are the 3 labels. Cache is, okay. Size of the cache is generally 2 kilobyte to 16 megabyte. So generally the L1 cache is the smaller one, L2 is the bigger than the L1, and L3 is the largest among the all three. Okay. Okay. Then cache, see this point. Cache is used to reduce the time to access an instruction from the main memory. Okay. So if you use the cache, because before the cache, the loading time of the instructions from the main memory is high. But if you have the cache, this latency reduced. Latency means the time required to move the data from the main memory to the registers. Okay. So this data, this time is reduced. Okay. And then this one, cache is working on the principle of locality of reference. What is this principle of locality of reference? This, what is this principle of locality of reference?
I can't really say, sir.
I'm asking, what is the meaning of this locality of,
Locality of reference.
yes, what is the meaning of this?
Locality of reference.
Okay, I'm coming. Okay, so please just see this diagram. You don't have to remember this diagram, only just think. So CPU access directly from the registers. This is your L1 label of the cache, then the L2 label of the cache, and then here is the L3 label of the cache. So
L3.
remember earlier you see these there are 4 cores or 2 cores. So each core has these L1 and L2 cache. Okay, and then L3 cache is shared by all the cores. Okay, so I'm not going in deep. I just put this diagram here. So if you want, you can go in depth about this diagram. Otherwise, it's not required. Okay, just remember each core has L1 and L2 cache, but L3 cache is shared by all the cores. Okay.
All the cores.
Just one thing. Locality of reference. I'm coming on that thing. Okay, so slides end. I'm just coming on the my notes.
Locality.
So coming on here. What is this locality of reference? This is the only concept left from reference. What is the meaning of this? Okay, I am giving you an example. How many phone number? What is the size of your contact list in your phone?
What's the size? It doesn't really have a size. Just
Means number
you
of
could
contacts.
put how much contacts.
Yes, number of contacts. What is the number of contacts in your cell phone? Not actual number, just some idea. About 200?
Yeah, it's about 200.
Around 200, something 100, maybe 100 or 150, something like that. Okay. How many? Okay, among these 200, how many persons you call daily?
Just maybe 2, 3, or 4.
Okay, maybe 4. And you just call these 4 persons repeatedly on daily basis. Today you call, maybe tomorrow you again call, maybe after 2 days you call. Only these 4 or 10 or 20 numbers. So among these 200 numbers, only 10 or 20 numbers you refer daily or routinely, regularly. What about these 180 numbers left? Among 200, these 20 numbers you've taken that you can use more frequently. But what about these 180 numbers? Maybe
I don't really call them as much.
Yeah, maybe after 1 month, 2 months, 3 months, sometime if you require something or
Yeah.
you can call them. It's not they are not important, but generally regularly you don't call them. So you actually working on the principle of locality of reference. Means locality of reference is says the statement of locality of reference is this. Generally, the memory referenced by the CPU is just a small amount of things. Okay, it's not going to refer if your program has 2000 kilobyte of size. It's just refer some in between regularly. It might be at any point, but it's not all. It's not the point that. Okay, again, let me. Okay. So locality of reference says this: if you access this point here, maybe you access the nearest point again. That is the meaning of locality of reference. Okay,
Mm-hmm.
getting the idea or not?
Slightly.
Okay,
But yeah, keep going with it.
okay. So locality of okay, locality of reference says this like if you read something from here, it's possible that again you read from at the same location at the location some above or below, not at the end point or at the beginning. That is the meaning of the locality of reference. Like the phone number, you just use 3 or 4 or 5 phone number regularly, not all. So if you have a long list of statements, this. So generally CPU tends to, it's just observed. If you read this instruction right now, it's probably that 2 or 4 instruction above or below, you read again. Next instruction read from this location, not at the bottom or not at the top. Okay. So this is the concept of locality of reference. It's coming in the section of your operating system. So if you want, you can refer any other operating system book or Wikipedia page. Maybe though they at those places you get a more idea. Okay.
All right, sir.
Okay. So solve some quiz questions. Okay. Okay. So quiz is visual.
This is fine. That's right there and no access.
Yes. Which of the following is not supported random access? So again, remember,
Yeah, come.
cache memory is SRAM. Register is SRAM. These two is already covered. This goes in the next section, but
So,
again, if you just see second slide, it's the primary memory. And primary memory generally use the random access. So the only option is compact disk. This is not a random access.
compactness.
Yeah, it's a sequential access.
It's sequential.
Yeah, this is a sequential. Okay, so this is the first one. The correct answer is D. Okay, go move to the question number 2. Which of the following requires to refresh after a few milliseconds?
The DRAM.
Yes. So, of course, registers and cache is the type of SRAM. Okay, and you already know that SRAM is not required to refresh. The answer is correct answer is DRAM. Done. Okay, the
Yeah.
number of bits in a 1 kilobyte. See the trickiness here. 1 kilobyte to okay. So in 1 kilobyte you have 1024 what byte, not bit.
Bit. Byte.
Yes, in 1 kilobyte you have 1024 byte, not bit. Here I am asking number of bits. So to and in byte how many bits is there? So 1 kilobyte you come to 1024
Yeah.
byte. Yes, byte means 8 bit. True, and it multiplied with the 1024.
Yeah.
Okay, so if you multiply it, and solve it, it comes to 8192. And otherwise, if you not, just see this is only number match here, 8192 bit. So that's the correct answer. Okay, you just multiply 1024 with 8 and it comes to 8192. Okay, coming to the question number 4, which of the following is the fastest memory?
The registers.
Yes, this is the fastest one. I already explained it. Which of the following memory supports sequential access but not random access? It supports only sequential access.
Hard disk.
Yeah, that's true. When I go in deep with the disk, I cover this thing, but the answer is the hard disk. Okay, these questions are from the quiz number 2. Okay, now this question number 6. Which of the following is not true regarding RAM? Just read.
Read and write from any location. Is true. Is volatile. Is true. Works on the principle of conflict of reference.
Yeah, this is one of the false. This one is a false statement. Yes. Okay. The RAM is not based on the principle of locality of reference. It's the cache memory. Okay. So, which is not true? This statement is not true. Okay.
Yes, sir.
Question number 7. Which of the following is not true regarding cache memory?
A. Some modern CPUs.
Yeah, that is not
Instead
true.
of some, it's supposed to be all.
Yeah. So this is point is supposed to be R. And this cache memory is working on the principle of locality of reference. That's a true statement. Cache memory used to reduce the time required to access data from the main memory. Okay, true. This is the definition of latency. Okay, so that's also true. And cache memory is the static random access memory. That's also true. Okay, so this statement A is the false one. Question number 8. Which of the following is true regarding the CPU register?
PCs and something. This one is true. D.
Okay, this statement is the true statement. Okay, see, registers are dynamic random access memory. No, these are the SRAMs. Okay, PC is the only register available in the CPU. That is also again the false. PC means here program counter. Okay, PC means program counter, and there are a lot of more registers. Memory address register, memory buffer register. So there are a lot of more registers. Okay, so I'm not going in deep, but there are a lot of registers.
Yes,
not
sir.
one. There are more than one register. So again, this statement is false. What about C? CPU sometimes loads data and instruction to the register. No, all the time. So this is again the false statement. Okay. So question number 8. The correct answer is D. Okay. Comes to the question number 9. Okay. 40 billion.
40 billion
Billion operation. Okay. And how many seconds? 10 seconds. Okay. So
10 seconds.
yeah, billion means giga. Okay. So billion and giga is the same thing. So just convert it. Billion means giga. 40 by 10. When you divide 40 to 10, it comes to 4. Okay.
4. Yes, sir.
4 giga and hertz is the same thing. Remember when I discussed about the speed is 2.0 gigahertz about the CPU? I told you it means 2.0 and then 2 and then
I remember.
you remember this? Yes. So same thing. So 40, just divide this 40 billion operations by the seconds. So if you divide it, it just come to the 4.
Then,
Okay. So this is the correct one.
yes.
Okay. Coming to the question number 10. You getting the idea of this problem or not? Still you are facing difficulty with this question. Mark? Mark? Can you hear me?
Hello.
Mark, you hear me?
Hello. I hearing you, sir.
Good. Uh-huh. So this is the last question. Question number.
Oh,
Okay. So can you get the answer for
yes.
this question or still you have facing problem with this question?
Still had problems.
Okay. So this is CPU A and this is CPU B. Okay. I just am putting the in chart so that thing is clear. Okay. CPU A frequency is for CPU A is 4.2 gigahertz. Okay.
Yes,
Okay.
sir.
And about this, uh, I think it's 4 gigahertz or 4.2 gigahertz in the question. Can you check?
It's
It's 4 gigahertz here. I think this is 4 gigahertz.
sorry.
Do you have this question?
No.
Okay. Suppose it's a 4 gigahertz. Otherwise, there is some problem. Suppose it's 4 gigahertz. Okay. Otherwise, this answer is changed. Maybe.
Mm.
So this is 4 gigahertz. This is 4.2 gigahertz. I take these both options. For the time being, just suppose this frequency of A is 4 gigahertz and frequency of B is 4.2 gigahertz. So clearly here, CPU B is winning. Yes or no? Because its frequency is high. Now, in terms of the turbo boosting, CPU A support turbo boosting. That's true, but CPU B doesn't support the turbo boosting. Okay, and then number of core. CPU A has the 4 core. CPU B has the 2 core. What about multi-threading? Multi-threading not supported here. Multi-threading supported here. So this two become 4 core. Yes or no? So which one win?
Or, yes.
Which one win? CPU B is winning in winning position.
Uh,
Due to the
B.
yes, due to the multi-threading, two CPU becomes the two physical CPU become 4.
Or,
Okay, so it has the speed of 4.2. It has the
yes.
4 effectively 4
Here.
to the multi-threading. And since the one more thing, even this speed is 4.2 gigahertz, this is same, but see, this is not a turbo boosting, and this is turbo boosting. Means it's not the always that you get this 4.2 gigahertz. Here you always get this 4.2 gigahertz. So in terms of the processor capability, B is the better option. Okay, although it has its own
Yes,
drawback.
sir.
You get the idea. So considering these all the 4 cases, The correct option is option D. Okay, means CPU
D.
bit. Yes. Now you get.
You know, I understand. Yeah.
Okay, good. So just so I today I stop here, and tomorrow we start with the more memory things like secondary memory and ROM. Okay.
All right, all right.
Okay, Mark.
All right, sir. Tomorrow then.
Yes, yes, yes. Yeah. Okay.